Hey guys. So now I want to talk about the Gram-Schmidt procedure. So Gram-Schmidt is going to require the orthogonal decomposition theorem that we saw earlier. Remember, the whole point of building inner products was to make these projections make sense. So we have the picture that if you have a vector u and you have a vector v, that you could pull u apart into orthogonal pieces, one of which points in the direction of v, and one of which is orthogonal to the direction of v, and that the sum of those vectors is equal to u. So I'm going to use colors to illustrate here. So this is how you produce this projection. So this vector right here we call CV, or if you like, it's the dot product of u with v over the dot product of v with v times v. And another name for this is the projection of u onto v. And this vector we call w. So this was w, and we can always define w by taking u and subtracting cv from it. And the point of this picture was that these two vectors were perpendicular to each other. cv is orthogonal to w. There's a 90-degree angle right here, just at least based on the picture. And further, that u can be rewritten as cv plus w. Okay, so the idea is that I can take u and v, and I can decompose u into a piece in the direction of v and a piece that's perpendicular to the direction of v. And this is going to be the core idea that we use when we're constructing, we're taking a basis and we're sort of straightening it out without changing the span. So here's the big idea of Gram-Schmidt. So let's just do it with two vectors. Suppose that you're given a basis for some vector space. Say it's vector subspace built out of two vectors. So you have a basis, v1 and v2. And what you would really like to do here is you would like to take v1 and v2, and you want to produce vectors e1 and e2 that are orthonormal. And the span of e1 and e2 is equal to the span of v1 and v2. This is sort of our objective. I want to get orthonormal vectors out of v1 and v2 that have the same span. So it's a basis for the same space is the idea. And so what the procedure looks like is this. E1 is really easy to find because we could just take v1 and normalize it. So we take e1 and we set it equal to v1 divided by the length of v1. So this is a unit vector in the direction of v1. Now, how we're going to get an e2? The idea is that if we have an e1, here's e1 right here, and we have v2 pointing in some other direction. Now, I know it can't be a multiple of e1 because these vectors started linearly independent. So v2 is not a combination of anything that came earlier in the list, which is e1. So where am I going to get a vector that has the same span, the vector e2, so the span of e1 and e2 are the same as the span of v1 and v2, but that is orthogonal to e1. And the idea is we're going to use projection to do it. If I project v2 down into the direction of e1, this vector right here is in the direction of v1. I don't want that. What I want is this vector, because this vector is orthogonal to e1. And the span, because that vector is a linear combination of e1 and v2, that's in the span of e1 and v2. That vector is not produced from the outside. I'm going to make that vector only using e1 and v2. So if I took this vector right here, say I call it w, and I normalized it by taking w divided by the length of w, this thing is going to be the e2. So the e2 is going to be this vector right here. That's the idea of the Gram-Schmidt process. So the way that you compute that is you say, well, what should e2 be? E2 should be equal to, I should take V2 and I should subtract from it the projection of V2 onto E1 in the direction of E1. That's this vector right here. So this quantity that I've written down right here, this quantity is this vector. Because what I've done is I've taken V2 and I've subtracted away the projection of V2 onto E1. But the thing I've got out the other side here is not a unit vector. So I could divide it by the length. Now that looks complicated, but remember, all we've done is we've produced this little vector right here. Now the claim is the span of E1 and E2 is equal to the span of V1 and V2, because everything in the list came from a linear combination of the previous vectors. That's basically it. How do we lift this up to more vectors? Well, now imagine that we have 3 vectors in the list. There's nothing stopping us from continuing this procedure sort of inductively. So how would it work in the 3 vector case? If we have a V1 and a V2 and a V3, and I want to orthogonalize this set, or I want to Gram-Schmidt it, then what I can do is the following. We're going to let E1 be equal to V1 divided by the length of V1. And for E2, we're going to do the same picture we had before. We're going to say, take V2, subtract the projection of V2 onto E1, make it a unit vector. How do I get E3? Well, take V3, make it perpendicular to V1 by subtracting off the projection onto E1. Make it perpendicular to E2 by subtracting off the projection onto E2. The thing that came out the other side might not be a unit vector, so make it one. So a 3-vector set is more steps, but the same idea applies, right? We start with E1 we get by just normalizing the first vector in the set. We take V2 and we do this with it, where we say, okay, I'm going to do this unit vector pointing out in this direction right here. In the E3 case, I do it twice because I have 2 vectors I need it to be perpendicular to. And so the point is, if I subtract the projection off onto E1 and I subtract the projection onto E2, then the vector that's remaining is orthogonal to both of them. It's part of the orthogonal decomposition theorem. And so the general theorem says that you can do this for any number of vectors, and that the result that comes out here, I mean, the point is E1, E2, and E3 is an orthonormal set. And the span of E1, E2, and E3 is equal to the span of V1, V2, and V3. The process of taking a basis and orthogonalizing is called the Gram-Schmidt process. So here's what the whole theorem says, the way that Axler states it. Suppose V1 up to Vn is a linearly independent list of vectors. In V, let E1 be equal to V1 divided by the length of V1. Then for M equals 2 up to N, we're going to do this recursively, which means start with 2 and then work your way up the list, because you need the second vector to get the third, and the first, second, and third to get the fourth, and so on. So define recursively. Ej is equal to the jth vector minus the projection of Ej onto E1 minus the projection of Vj onto Vj minus 1. And then take all that and make sure it's a unit vector. And that's what the process says. Then E1 to En is orthonormal. And the span of E1 to En is equal to the span of E1 to E. And yeah, in practice, this is kind of a pain in the butt, which is why there's numerical algorithms that do this when you need to. In practice, what it means is that what mathematicians will often do, as I mentioned in class, was just work with an orthonormal basis, because if you give me a basis, I might as well choose it to be orthonormal. And the Gram-Schmidt process means that we can do that. In fact, we can say more. There's some really immediate consequences here of the Gram-Schmidt process that are highly useful from a theoretical standpoint, which is, well, since every finite dimensional vector space has a basis, and I can take any basis and orthogonalize it, then that means actually every finite dimensional inner product space has an orthonormal basis. So that's the theorem. Every finite dimensional inner product space has an orthonormal basis. And the proof here follows from the fact that every finite dimensional vector space has a basis. And then just apply Gram-Schmidt. And then notice the fact that the inner product exists here is an important part of this calculation. Okay. And then the final theorem I want to talk about here is not only does a vector space come with automatically an orthonormal basis, but because any linearly independent list can be extended to be a basis of a vector space by the basis extension theorem, literally the same theorem is true in that case too. So if you start with an orthonormal list, you can automatically extend it to an orthonormal basis. Any orthonormal list in an inner product space V can be extended. Finite dimensional, sorry, careful here. In an inner product space V, and a finite dimensional inner product space V can be extended to an orthonormal basis. And this is just by the extension theorem. The idea here is that if you start with an orthonormal list, in fact, here's sort of a walkthrough of this proof. If E1 to En is an orthonormal list, then of course E1 through En is a linearly independent list, because every orthonormal list is linearly independent. Then the extension theorem says that you can take E1 to En and you can extend it with, say, I don't know, F1 to Fm, extension to a basis for V. Now you've got a basis for a vector space, and every basis can be orthogonalized by Gram-Schmidt, which means that this can be orthogonalized into a basis E1 up to En plus 1 up to, or whatever we're going to call it, En plus M by Gram-Schmidt. So if you want to know anything of, like, if you wanted like to upshot of like what the point of all this is, or what the big thematic thing here is, inner product spaces are awesome. And I would strongly, well, not strongly, I'd say like the ideas here also in a lot of ways carried forward even into the infinite dimensional spaces that get used in higher level analysis and in applied mathematics as well. So inner product spaces are great. As soon as you get the inner product, you get geometry of angle and length, and you should be able to see here that like just getting angle and length has given us the ability to build a ton of structure into vector spaces that is not there if the inner product isn't present. Okay, so that's sort of a walkthrough of 6b. There is more in 6b. I'm not going to make a point of looking at it. I'm going to go back sure and look at the homework and make sure I didn't accidentally include any questions about that stuff. The next and last subject of the class is section 6c. So yeah, thanks for listening. See you guys.